Okay, and we are back. Happy Monday, July 6th. I'll take this off. Monday, July 6th, chapter 19. We're moving along. Carboxylic acids, hard to believe there. This is part one. Test one is due today. Remember, July 6th is our first midterm exam. It's 40 multiple choice questions. There's a PDF in the file on Learning Suite under content. I'm sure you've looked around and seen that now and know where that is, but make sure you get that answer sheet filled out and then scanned and uploaded by tonight at 11:59. So you only need to turn in the answer sheet, not the rest of the exam. So you just look at the PDF there and enter your multiple choice scores. And also, we'll actually be finishing chapter 19 today. It's only a 2-class period chapter, so the homework associated with it, homework 4, is also due, not today, no, we're giving you an extra day. Okay, we don't want it due the same day as the test. So yeah, it's due tomorrow, and that gives you a little time to talk to the TAs. So yeah, so make sure you zoom in and get some help there as needed. But yeah, keeping up on the homework. Sorry about the breakneck speed of the term here. That's the nature of the beast. We've warned you about that, and hopefully you're okay with that now. Let's see, chapter 19, what we'll need to know, looking at the overhead up here. I always like to give the chapter summaries. So carboxylic acids, we've heard about these functional groups before. We've seen them, we've been using them at different points, but now we have a dedicated chapter because they're so versatile and so useful. We'll see them many times throughout the rest of the term, and you'll see them moving forward in biochemistry also, and other molecular biology classes, or what other kind of technical class you have at the molecular level. Carboxylic acids will feature prominently. They're unique among functional groups. Well, the amines also ionize. You could say the amines and carboxylic acids are the ones that ionize under normal aqueous conditions. So you have to know what conditions, what pH you're at to figure out whether it's ionized or not, charged or not. So it's a little bit tricky to keep track of that. The resonance effect stabilizes the conjugate base. They're very polar, high boiling in general. We'll talk about the IR, which, because it's a hydroxyl group, the neutral form here, absorbs at 3,500, and also the carbonyl group, carboxylic acid, 1750. NMR can kind of be spread out, and it can show up anywhere from 9 or 10 up to even 15. And sometimes it's so spread out by hydrogen bonding, you don't even see the proton from a carboxylic acid. The name, alkanoic acid, there's some common names you'll need to know here. I list some of them. Formic acid, well, these are the only common ones you need to know. Formic, acetic, butyric, steric, oleic, benzoic. Benzoic acid we already looked at, right, in chapter 17. So we'll tie some things in here. Cyclic ones are a little bit different to name. They're called cycloalkane carboxylic acids. So they're a little bit different. And then we have the diacids, straight chain parent, but 2 acids on the end. And this is the oxalic, malonic, succinic, glutaric, adipic, and pimelic series. And I do expect you to know those. Why? Because they have unique reactivity in many cases, and they feature prominently in metabolism moving forward. So you need to know the names of those. So here's the basic reactivity of any carboxylic acid. We show acetic acid with base going to the conjugate base, which is the acetate or the carboxylate, and you see the resonance effect here, right? Which stabilizes that. And the degree to which any conjugate base is stabilized means that the original acid becomes stronger. So the more stabilizing that conjugate base is, and by resonance here, certainly a carboxylic acid is stabilized relative to other hydroxy acids. We'll compare this to alcohols and others. The pKa here is around 5. For acetic acid, I think specifically it's 4.8, whatever. We'll have some other examples here, including some drugs and prostaglandins, and we'll relate this to amino acids. There's a different section coming up. We'll show the prep of different acids. You already know some of these methods we've already covered: oxidation of primary alcohols, and some other things there. Reactivity, we've been talking about the pKa5, the resonance stabilized conjugate base. There it is again. How they react with different reagents. They do react with nucleophiles. We'll see that later on in another section. We'll see what other factors affect the stability of carboxylic acid. It's not just the resonance effect. There's also inductive effects that can be stabilizing. We'll relate this to other hydroxy acids, alcohols, pK16, phenol 10 there. Henderson-Hasselbalch equation, I'll show you that. I don't expect you to derive that or anything, but I expect you to know how to use that and see qualitatively the extent of ionization. We'll also use the pKa, the formation of the carboxylate, to look at extractions, to be able to separate different compounds based on this ionization effect. Related acids in organic chemistry are the sulfonic acids. We showed you how to sulfonate benzene. We've talked about tosic acid before. Phosphoric acids are another class of organic acids, as long as the R group here is based on carbon. The pKa of sulfonic acid is very low, so those are super strong, very strong acids. Phosphates, not as much. Phosphoric acids will feature prominently in biology, so we'll show some of those. And then amino acids. This combines the two ionizable groups, right? The carboxylic acid and the ammonium group. And of course, amino acids are the key building blocks for proteins. Most of molecular biology and what you'll be looking at in metabolism and other things later on in biochemistry will all relate to amino acids, peptides, and proteins. So look at the basics of that, the structure, and some of those things. Now, just to catch your attention a little more, we've got the Hall of Fame. Different carboxylic acids. You've probably heard of some of these. Well, you've heard of at least acetic acid. How about tartaric acid, the tart flavoring thing in candy? You've all tasted that. And there it is. That's in neutral form. So that would be at low pH, keeping it protonated, tartaric acid. A couple stereocenters there. Citric acid, you've probably heard of the citric acid cycle already, or citrate. Citrus fruits, yeah, they feature prominently in lemons and oranges. There it is. Niacin, one of the key vitamins, vitamin B3. The niacins, the Bs are all nitrogen-containing cofactors in biology, different reactions. You've heard of aspirin, of course. It's a benzoic acid with an extra ester on it. Glutamate, this is a nice one. This is one of the 20 amino acids involved in protein formation. It's also a flavorant in food. It's the umami flavor or the meaty flavor, which is kind of fun. You've probably heard of MSG or monosodium glutamate. Pyruvate, tryptophan, Cipro, this is one of the newer generation antibiotics. NutraSweet, artificial sweetener here. Prostaglandin, we'll look at those. These mediate different signals upon injury in the body. Oleic acid, the monounsaturated long-chain fatty acid. Okay, so this has properties of being polar here due to the carboxylate, but also being non-polar due to the long hydrocarbon chain. We'll look at the factors that affect that, of having this amphiphilic character, polar and non-polar in the same molecule. Ascorbic acid, another vitamin. Which one is it? Vitamin C. Very good. The water-soluble radical quencher. Then we got the Hall of Shame. We got the fame. We got to take the good with the bad, I guess. Well, these molecules aren't bad on their own. They're maybe used inappropriately or have bad effects that can be bothersome. Butyric acid. You emit that all the time. That's body odor. Okay. It's actually not produced by you. It's produced by bacteria on your skin. And then we got formic acid produced by ants and other stinging insects. We got gamma hydroxybutyric acid, which is an abused drug. Simple drug, isn't it? Caproic acid, also produced in animals. Goats and deer and other animals like that have a pungent smell. Perfluorooctanoic acid is a plasticizer in different materials, has some hormonal effects. It's being phased out. Lactate, upon metabolism, If you don't have enough oxygen in your blood, if you're not oxygenated enough, this builds up in the muscles and gives cramping, that cramped feeling. So this is a carboxylate. So this is at higher pH, and higher means just above its pKa, right? So this is even present as a carboxylate at pH 7, which is physiological conditions. Now we have a couple nasty toxins here. This one from cyanobacteria. Lysergic acid from rye, ergot rye on grains. Trans fat, which comes out of the industrial process. This is metabolized in the body such that it gives more free radical damage, can lead to heart problems. This one, humble little molecule, cyclopropene carboxylic acid from mushrooms, causes a muscle wasting disease. Phthalic acid, another plasticizer. Demonic acid, yeah, that sounds evil, doesn't it? Paralytic shellfish poisoning, that is an evil disease. So carboxylic acids, there's 3 of them right there, right? And MSG, I mentioned that in food. This has a nice umami, meaty flavor to it. Problem is sometimes chefs add too much, and some people are sensitive to it. It's not inherently toxic on its own, but yeah, MSG. People have heard about that. Anyway, and tetrodotoxin, the pufferfish toxin. Where's the carboxylic acid here? Well, it's tied up as an orthoester right here, this acetal. And the rest is just a guanidinium cation and a bunch of hydroxyls. But actually, the carboxylate's masked. It's right there, part of that. Anyway, so maybe that catches your attention. Let's look over here and maybe do a demonstration to start out with. This is a humble little acid here, acrylic acid or propenoic acid when we get to the specific naming here. Now this has an alkene and a carboxylic acid, highly functionalized, right? So we can polymerize that. Chapter 15, react that with peroxide and heat or light, and we can make the polyacrylic acid. And so the X there means what? A bunch of repeating units of the acrylates being polymerized on there. That's the neutral form of the acid. If you treat that acid with sodium hydroxide, you make the sodium salt form of the carboxylate. Now this has some unique properties. Let's see here. It's a polymer. The chain up here is nonpolar, but the charge parts, especially down here, and the sodium salt that goes along with it are what? Very hydrophilic. So this will aggressively grab onto water. And let's see how aggressively it might grab onto here. So I'll just fill up a beaker here with about 400 mils of water. And I'll add in, about a gram of this material. And let's see if they gave me a spatula. No, they didn't. That's okay. We'll just add in a gram of this stuff right here. Okay. This is a sodium acrylate polymer. About a gram of it. There we go. And let's stir it. Let's see. Remember that was pure water. Oh, look at that. The stir rod stands straight up. And look at this. Oh, look at that. It's like a milkshake at your favorite milkshake stand. That grabbed all that water instantly. Effectively, it can absorb over 10,000 times its own weight in water. Now, where would that material want to be applied at? Very good, in diapers. Okay. It's called superabsorbent material. When this material was invented about 40 years ago, remember diapers used to be just cloth diapers, and the leakage get everywhere, and men would never change diapers. So I like to point out that this compound right here has done more to save marriages than any other compound I know. Why? Because men will now change diapers, knowing it will be easily absorbed there. All right, let's get into some of the real stuff we need to know. Okay, so carboxylic acids, and this is kind of the crux of the whole story right here. Neutral form or carboxylate form. Now notice this is different. This is neutral, right? Okay, and this is charged. That's going to change the properties quite a bit. We have a chain over here, which can be very long. Acetic acid, that's not a big deal. It's just a methyl. But we'll see a lot of carboxylic acids that can change that. So I have the polar group and the ionizable group. So because this has a pKa of about 5, and that's one number you have to know, okay? And that relates to the pH if you're in an aqueous solution. Now, pH refers to the concentration of hydronium ion in water. So we'll need to redefine that, and we'll look at that very specifically. pKa refers to a specific compound. So it's how this compound reacts to the pH state in which it's found, okay? So if we're up here above pH 5, say we're at pH 7 or 10 or 12, super basic side here. Remember, pH is an inverse scale, right? So it goes from 0 up here to 14, which is very high concentration. In fact, molarity of hydroxide at pH 14 is what? 1 molar. If we're down here at pH 0, that means the concentration of hydronium ion is 1 molar, okay? But you put these different organic compounds now in these aqueous solutions at different pHs, and they'll respond. If we're greater than the pKa of carboxylic acid 5, it's going to be carboxylate. It's going to be completely ionized. So that's something we need to keep track of. Now, when we look at amino acids, we're going to have 2 ionizing groups, right? We'll have different side chains, these R groups. There's up to 20 different amino acids. And what? We have this one that can ionize and this one. Well, the amine, we'll have separate chapters on the amines. But the first thing to recognize is amines are basic and carboxylic acids are acidic, so it can donate that proton. And we'll look at this form. It's still neutral overall, but this Zwitter ionic form is how usually the amino acids exist. Why? Because the base is strong enough to grab a proton off there, and it can exist as this internally charged structure where one side is negative, one side is positive. But this can change, right? If we go to low pH, we can what? We can protonate the carboxylic acid. And now this amino acid becomes what? +1 charged overall, okay? So we need to keep track of it. If we're down here at pH 2 or 3, it exists like this. But if we're at high pH, and this is where we have a lot of hydroxide, we can take this proton off here, okay? So this pKa right here for this acid is what, 5? And again, we'll go through some specifics of this. I'm just meaning to introduce this. pKa here of an ammonium cation, this is 9. But if we're at high pH, if we're up around 10 or 12, what? This can get pulled off, and now it's NH2, it's neutral. But we still have, of course, this guy ionized, right? Because that's more basic than its pKa. So overall, this is what? -1. So we see a lot of differences here. The Zwitter ion, overall charge is 0, low pH +1, high pH -1. Why? Has to do with the structure, okay? The stability of that conjugate base and electronegativity and other factors associated with the structure. Everything goes back to structure. Now, before we get into the details of 19, sorry, I'd like to give you a little more introduction here to this next section that we're covering, chapters 19 through 22. So everything's right here in 19. Carboxylic acids, and some other things that we formed from that carboxylic acid acid chlorides that we saw for Friedel-Crafts acylation. We'll relate that back to the previous topic there. 20, we continue with carbonyl compounds, but we'll be limited to aldehydes and ketones, okay? Now, aldehydes and ketones are similar to carboxylic acids in that they have a carbonyl, but they don't have the OH group, okay? They're not acidic like carboxylic acids, but they can undergo reactions with nucleophiles. So if we have a strong enough nucleophile, we can add here, give different products. It will look like this, right? Okay, so different type of reactivity. Chapter 20. 21, we'll have the nucleophiles here being amines, okay? So we'll have primary amines, secondary amines, reacting with aldehydes and ketones with this same paradigm, same thing, lone pair on the amine, being able to add. But the products will be a little different, okay? But this ties in with the topic of carbonyl compounds, okay? And then 22, we'll look at more details of all the derivatives of carboxylic acids. And what do we mean by derivative? We mean they can easily be made from carboxylic acids. These X groups can be a lot of things. X can be halide. X can be OH. That's carboxylic acid, right? X can be OR. That will be an ester. X can be an amine. That would be an amide. So there's a lot of different groups that will come out of that. I think that's a good summary of that for you. Looking forward to the next 4 chapters. All right, let's move that up. Yeah, just stay focused on this bottom one. So let's see, carboxylic acids. And I'd like to look ahead to these derivatives in 22 and just give you a heads up in what we're looking at structure-wise and what you'll see here. So here's the acid chloride that we used previously, right? These will be the most reactive derivatives, okay? We'll see a reactivity is very high here for these. Now, another high reactive derivative are the anhydrides. And we actually saw those in Friedel-Crafts chemistry also. They're also very reactive. And it has to do with you've got, a carboxylate group on the side of the carbonyl. Here you have a chloride on the side of the carbonyl. How about this one? This is very common actually in biology. It's called a thioester. They're also quite reactive. They're not as reactive as anhydrides and acid chlorides, but thioesters, we have sulfur here on an acyl group, can also be reactive. Now the next ones to look at are the regular esters. You've probably heard about these. We just looked at them as functional groups in 351. We'll have more details now on esters. They're not as reactive as some other derivatives we'll see, but they are quite reactive. You can transform them. We'll see a lot of reactions with esters. They're not as reactive as acid chloride. You might think, well, that potentially is a leaving group, that oxygen, but it's not as good as a chloride leaving group, okay? And then we have carboxylic acids themselves, where, it's an OH versus an O-alkoxy group on the carbonyl. And then we have amides. We'll throw in a couple others later on. Amides turn out to be the most stable carboxylic acid derivative. They have some extra resonance effects, and it's a poorer leaving group. So it'll be a combination of factors we'll look at. I like to point this out early on in this section because they're all carbonyl related to carboxylic acid, okay, which is the topic here in 19. So I like to show that ahead of time. Let's look at the structure and the bonding in carboxylic acids. You already see what the structure is, right? So we've got an OH group, we've got a carbonyl, and I like to draw it with a little 3D comparison here. So remember, the pi bond is, of course, the p atomic orbitals, right? So there's your pi bond, right? You also have a sigma bond down there, right? Well, what about the OH group? Well, we can hybridize that oxygen such that what? We've got one lone pair and a p atomic orbital, right? And one lone pair maybe in an sp2. So maybe we've rehybridized that oxygen. Why would I want to do that? Well, you can see then we've got overlap here, right? In fact, we can draw that resonance structure, right? Where we've got O minus, we got double bond there. Even though we haven't taken the proton off that oxygen yet, that would be an important resonance contributor to that shows something about the structure in that flat region between the molecule. Let's look at some physical properties here now to relate this to carbonyl compounds and ultimately carboxylic acids in general. How about this progression here on boiling points in degrees Celsius. So an alkene here, 1, 2, 3, 4, 5 carbons, comparable in molecular weight to all of these things. So I think this boiling point points out how polar they are and what the intermolecular forces might be. What would you say there with an alkene? Just a pi bond, and everything else is just carbon-hydrogen bond. Well, not very polar at all, right? So boiling point, 31 degrees C. Yeah, at room temperature, which is what, about 25 degrees Celsius, this is indeed a liquid, but not by much. You warm this up on a summer day in Tucson, this compound's a gas, right? It's gone. So you're very close between the liquid and the vapor phase there. What about a ketone here? Comparable molecular weight, 80 degrees C. Right, we have a polar covalent bond there. We have a partial positive end, partial negative end, okay? So those properties we can say in the condensed phase and the liquid phase, partial positive end can get close to the partial negative end and have stronger intermolecular forces that require more energy to break those up and to vaporize that, make it boil. What about the alcohol? Yep, higher still, 99 degrees for that one. And why? Well, now we have hydrogen bonding, right? We have a electropositive small atom on a very electronegative atom, oxygen, right? So you got the partial positive end, partial negative end, and that's much stronger. Well, quite a bit stronger, you can say. What about carboxylic acids? What about this guy? Whoa, 141 degrees C for the boiling point of propanoic acid. Why? Why is it so much higher? Well, hydrogen bonding, polar, and we need to point out one other effect here. That is, in the condensed phase, you can have a lot of this occurring. What? You've got the right geometry for a dimeric structure with intermolecular, hydrogen bond there that has the right geometry that goes a little bit beyond simple hydrogen bonding of alcohols. So carboxylic acids are very high boiling, and we can see that there quite easily. All right, let's get into the ionization. What we need to know here, a little bit on this. So here's the first reaction with acetic acid. Can we donate that proton to water? And it's a reversible reaction, but what degree does it lie, either to the left or to the right? So we define this as the acid Ka equilibrium constant. So, you know, we can define these things quite readily, right? We got the Ka, which is equal to the concentration of acetate times the concentration of water. Those are the products divided by the starting materials, which would be concentration of acid and water. Do we leave that in the denominator? No, it's a Ka, so we leave out the water. These are normally under dilute conditions, so the concentration of water stays the same. And what is this here? Well, it turns out to be 10 to the minus 5. Okay. So is that a favored reaction? No, that's a small thing. This is 0.00001, right? So very small number. So it means the concentration, the products is very low compared to the concentration of the starting material. So where does this equilibrium lie? It lies far to the left, okay? Now we can compare that to some other acids here, like HCl. What's the ionization of that with water? If we have that there, well, that's 10 to the 5th, okay? And because these numbers are so large, and this is a hallmark of what? A strong protic acid, so very high number. This is 10,000, right? So we redefine these numbers as the pKa's. The pKa equals minus the log of the Ka. So we have this logarithmic value, and it's a minus number here, so it's an inverse scale. So this becomes what? pKa for acetic acid here is what? 5. Well, actually, it's 4.8 if you look at the exact number, but it's okay to know that ballpark number. Most carboxylic acids are right around there, 5. What about HCl? If you take the minus log of this, its pKa is what? -5. Super strong acid. And we can see some others that are super, super strong there. So let's get back to that in a second. Like I'd like to do now is nomenclature. And just a little bit on nomenclature. I'm not going to do a big deal here. The parent is alkane. What we do is we take off the E here and we go to alkanoic, add OIC, space, and then acid. Okay, so that's the new suffix to the name there. So the parent there, alkane. And the thing about carboxylic acids on a straight chain, it always gets number 1, and it has the highest priority. And that means everything else is numbered, including alcohols and alkenes and everything else now, in relation to the carboxylic acid being on the end, which has number 1. So let's look at the simplest one here. That would be this. I just gave you the common name to that, right? Formic acid. But we can use the IUPAC name of naming this. How many carbons do we have here? Just 1. So this is methanoic acid. And like I said, formic is okay. Okay, formic acid. Formiga, it comes from a Latin term meaning ants. And red ants produce copious amounts of that. Other stinging insects too. What about this one? Well, you know that is acetic acid, right? And that's what all chemists call that, acetic acid. But you could name it by the systematic name, ethanoic. Okay. Let's get into a couple more here. How about this one? I already said the name. Propanoic acid from propane oic acid. Okay. Let's see. Get another view here. How about this one? We've got 4-butanoic acid, or butyric acid. That's the common name for that. And going up, pentanoic acid. Let's skip ahead to 6. That would be hexanoic acid. Okay. And how about this guy? The one we had right at the beginning. So it's got an alkene also in it. And that's okay. You can modify the parent, right? Instead of propanoic acid, it's propenoic acid. And do you really need a number here? Well, this is 1 here. The 2 position is the only other place you can have the double bond. So the alkene part is really redundant there. But a lot of times you'll need a number if you're naming an alkenoic acid. Okay, so it's okay. You can name those different ways there. How about a long chain one? How about 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18. Long chain fatty acid, we call these. It has 18 here. This is stearic acid. And where does that come from? Well, from beef tallow, from lard, from animals there. A lot of animals have these saturated type of fats, and some have the unsaturated type. Let's look at the monounsaturated one. That's where we've got double bond here. And it still has 18 carbons there, but at the 9 position, we have a cis double bond, and it's almost always cis. Okay, there are some trans fats, but this is oleic acid. Your monounsaturated fat, we'll see that in plant oils. These almost always exist as acyl triglycerides, which are triesters of glycerol. We'll see that later on. If you make the carboxylic acid form of this and ionize that to the salt, just treat with sodium hydroxide. This is soap now. This can form micelles to have a cleaning action on the surfaces of different greasy or stained materials there. So we'll see the reaction of that and the structure of my cells and how that relates. If we've got cyclic carboxylic acids, so we can have a carboxylic acid here, cyclohexane, for example, and these are named as cyclohexane carboxylic acid. Okay, and if you have any other cyclic thing there, you just name it as that. These are a little bit different now. This becomes the one position, so if you number anything from that, that's where the one position is. It's similar to benzene naming there. But we're not going to drive you nuts with a bunch of things like that. Let's look at the dicarboxylic acids now. And these, like I said, are important for biology and metabolism. You can have this one, which has 2 carboxylic acids and only 2 carbons. This is oxalic acid. Okay. Oxalic acid is accepted by the IUPAC for the name of that, oxalic acid. Let's see, calcium oxalate, the calcium form here with the dianion, that's kidney stones. You actually see a lot of different variations of these in the protonated form and the ionized form. Usually at pH 7, these are fully ionized. It's a carboxylate form. So I'm drawing them as the neutral form right now. So that's oxalic acid. Then we've got malonic acid. And I'll just put the name here of this. Malonic acid has 3 carbons. So you have an extra methylene in between. That's malonic acid. Then we have succinic acid, which has 4 carbons. Succinic acid will feature prominently in the citric acid cycle. We'll see later on, again, 4 carbons total and 2 carboxylics. They have to be on the end, right, to be a carboxylic acid that way. Then we got glutaric acid. Looks like this. Glutaric. And let's see, adipic. 1, 2, 3, 4, 5, 6. Adipic. It's prominent in apples and other fruits. And let's see, one more. Sorry, pimelic. Pimelic acid's going to have 7. 1, 2, 3, 4, 6, 7. Pimelic. Okay, now you have these structures in your book. You can look them up anywhere. Why am I writing them up here? And I'm going to try to help you remember these. I'm going to give you a mnemonic device, and you never forget them. Okay, this is how I learned them. And when you get into metabolism and biochemistry, when these pop up all the time, you'll already know the name and be able to handle it. So here's the mnemonic: OMSGAP. Okay, so here it is. Oh my, such good apple pie. Okay. Oh my, such good apple pie. That lets you instantly remember all the names. Oxalic, malonic, succinic, glutaric, adipic, and pimelic. Okay, we'll torment you later with these as they come up, but I like to show it up front so you know what it is and you can keep track of it to begin with. All right, let's look at preparations of carboxylic acids. You've already seen a lot of these. You can take a primary alcohol, and it has to be primary, right? And if you treat it with chromic acid or dichromate sulfuric acid or chromium trioxide, any of those strong oxidants will take it all the way to the carboxylic acid. Okay, it has to be a primary alcohol because it has to get fully oxidized there. You don't need another mechanism. We haven't covered that or anything. From chapter, which one was it? Chapter, 18, the one on the test today. This topic here. So you can take this same chromic acid or potassium permanganate, and that will let you go to the carboxylic acid. And what's the name of that one again? Benzoic acid. Okay, so that's a reaction you need to remember. There's one from 351, another one here. and that's ozone. If we do ozone and water and let this work up, we create, in this case, this one's symmetric with the two methyls there. We create two acetic acids there. Okay, so that's the preparation of carboxylic acids. Let's look at some of the fundamentals of reactivity of carboxylic acids. So you can take acetic acid, sodium hydroxide, and react that to form sodium acetate and what? Water. Now, is this equilibrium? Which side does it lie on? And this is reactions of carboxylic acids. It's a proton transfer. So you got hydroxide, sodium here. Go ahead, grab the proton there. That forms, the sodium carboxylate and water. How are we going to figure this out and know the degree to which that goes? Is this equilibrium? That's where the pKa values come in handy, right? pKa here is 5. And we need to know the pK of something on this side. We need to know the conjugate, acid from the base over here. And we compare the two acids to see which side will favor, right? Where's the acid here? Well, it's water, pK of 15. So how do we figure this out? Remember, it's an inverse scale. So the higher the number means what? The weaker that acid, right? And this means we go to the side of the weaker acid. Why is that? Because the stronger acid relative to it has the higher capacity to transfer that proton. That's what we mean by comparing the two things. What about the magnitude of this equilibrium constant for this reaction? Can we figure that out? Yeah. You take the pKa on the right minus the pKa on the left, okay? And that will give you an approximate, we'll say, K for the reaction. So let's see, what does this look like? The one on the right's 15 minus the one on the left is 1. Now you can go through the Henderson-Hasselbalch equation and derive this mathematically, but this is just a quick back of the envelope estimation here of this equilibrium. So 15 minus 5 equals 10, and then you take 10 to that power, whatever this expression comes out. So the K then winds up being, well, that's 10. So your K equals approximately 10 to the 10 power for this reaction. Remember, it's a log scale, so these are huge numbers. So we took the log of the result here of the difference. And so what does this mean? It means it strongly favors the thing to the right. So here's sodium acetate, okay? Reacting for that. So that's the first reaction we're going to look at. We can react it with other things and talk about that type of reactivity. What else can we do with carboxylic acids? Well, if we treat them with super strong acids, now what do we get? So here's sulfuric acid with acetic acid. Which acid are we going to use here? Well, we're going to protonate from sulfuric acid onto this. And so acetic acid becomes a base. And that might sound kind of funny, but we need to compare the pKa's here, right? So we can go to this product, and there we have plus charge on that carbonyl because it has that proton there. And what's our conjugate base here from that? Well, it's bisulfate, okay? So why is this favored? Well, this pKa here is minus 7. Well, to really be accurate here, we need to look at this and say, minus 7, and what's the pK of this? That's a different species now, right? This is minus 2. So let's see, we have minus 2 minus a minus 7, and overall this is 5. So the K for this reaction right here equals 10 to the 5th power. So that's favored, okay? This is the acid here on the left. This is the acid on the right. And that pKa is also known. It's minus 2. And so you can estimate that. Yeah, a strong enough acid can function as an acid there. We'll see later on some reactions of carboxylic acids with nucleophiles. It's just one other one I wanted to point out here. If you have the sodium salt carboxylic acid and react it with a primary leaving group, what do you get here? Now don't forget this reaction. This is what? This is sodium iodide as our byproduct here. What type of reaction is this? Very good. It's SN2, right? Here we have a charged nucleophile, stable charge nucleophile. Here we have primary, good leaving group. Yeah, SN2 to make the ester. That's one of the reactions we had before. All right, a little more on properties, and then we'll wrap up here for the first hour. Give you a break here in a second. I like to look at some properties here, and that is solubility. So let's see. If we have small enough carboxylic acid, what about solubility in water? So acetic acid, how soluble is that? Well, it turns out it's infinitely soluble. That little symbol means at all proportions, infinitely soluble. What about butyric acid? Yeah, that one also infinitely soluble. But let's get up to something quite a bit longer. 1, 2, 3, 4, 5, 6, 7. Decanoic acid, okay? 10 carbons. What about the solubility here? Well, it's only 0.003 grams per 100 mils, okay? The smaller carboxylic acids, and it's what, 4, 5 carbons and less? 5, the 5 carbon rule. 5 and less is always soluble if you've got a polar enough group, and we certainly do here. But here we have more than the 5, right? And so the solubility drops way off here. What about this one? Now this causes you to think a little bit. Benzoic acid. How soluble in water is that going to be? How many carbons? Well, we've got 6 here. That's beyond the 5 carbon rule. So it's probably a lot lower, and indeed it is. 0.2 grams per 100 milliliters. 100 milliliters is about 2.5 ounces of liquid there. Let's see, though, this. What if we go to this salt form? Now, I'm going to give you a couple numbers here that might look a little funny, but the salt form, now we have, charge, polar groups here. And when we have a salt here, it's very soluble in water, but there is a limit. If you pack in more of this salt material, and on its own, it is a salt, and we'll show you that here in a second. There is a limit here, and this is 100 grams can go into 100 mils of water. If you go beyond that, it'll precipitate out and float to the bottom, okay? Now, what about benzoic acid? Now, remember, benzoic acid neutral form was not very soluble. Let's go to sodium benzoate, which is a food preservative, by the way. I won't always draw the opposite charges. Sometimes we just draw it, in neutral form, but it's not neutral. The metal's always cationic, okay? So sodium benzoate here. What about its solubility? Well, it's not infinitely soluble, but it's more than the neutral form. The neutral form is only 0.2 grams per 100 mils. This one, though, is 60 grams per 100 mils, okay? So it becomes much more soluble, okay, if we have it ionized to that form. And same thing with these, okay? This one's sparingly soluble, but it'll become much more soluble. Well, it'll form a micelle, actually. We'll look at those structures if it's in the ionized form. So keeping track of some of these numbers can be useful. Let me show you how this is used in a practical sense, and then we'll wrap up with a demo here in a second. We don't want to go over too much there. Let's say we've got benzyl alcohol and we've got benzoic acid. We want to separate those. Now, they have different boiling points. We could set up a boiling point apparatus. We could chromatograph them to separate those apart. But we've got a one-to-one mixture now, and we want to do the simplest thing. Chemists are lazy. We want to do the easiest, simplest thing. And we can take advantage of the ionization potential of carboxylic acid versus an alcohol. Alcohol pKa is 15, or 18, really. It's higher than water. It's less acidic. Carboxylic acid, benzoic acid, it's about 4.2, okay? So let's take this and react in water. Sodium hydroxide, both of these, okay? And then we're also going to have in here ether. Ether is a liquid material, and we're going to have water down here, okay? So when we do this reaction here, we're going to have in our glassware, we're going to use a separatory funnel. It's going to have a place to stop it from flowing through here. And the upper layer, where our ether is, we're going to have the neutral benzyl alcohol. But down here in the water, which has sodium hydroxide, we're going to have what? We're going to have the carboxylate, salt, okay? Remember, that's much more soluble when it's ionized. So now we can separate these two, right? We can draw this down, open up the valve here, and bring this down so that we'll have a water solution in our beaker, okay, of water and sodium hydroxide still. So we have excess sodium hydroxide. And our sodium benzoate, okay? Then we're going to take that and we're going to add more ether, okay? And we're going to add acid. We're going to neutralize all of the sodium hydroxide, and we're going to have enough acid in there, what? To get the neutral benzoic acid back in pure form. All we've got to do is eliminate the ether, and we can easily do that on a rotary evaporator, it's called, or rotovap, whatever. And so we have the pure carboxylic acid now. Well, where did the ether layer here go? Well, we can separate that. Once we draw this down here, we then have a separate flask where we just have the ether and the benzyl alcohol, okay? And we just take the ether off that. That's that original layer there. Here's our aqueous layer that's basic, right? And we take that off. What's this called again? This is called extraction, okay? Using the ionization ability of the different materials to get that to come out. All right, let's show you this graphically here. We've got the sodium acetate there, the diaper material. Look at that, it's still hanging on to that water. It's not going anywhere. Let's look at this. This is pure acetic acid. And what do you notice there? It's a liquid, okay? Where do we see acetic acid commonly? Yeah, in the kitchen. What do we call acetic acid in water? It's called vinegar, okay? Smells like a bad salad bar, okay? There it is. Whoa. Oh, yeah, very pungent, sour smelling, and strong vapor. Vinegar is only about a 5% acetic acid in water solution. This is glacial acetic acid, 100%. So that's really cleaning out my nose right now. And what is this? This is sodium acetate. So this is different, okay? Vinegar is this, acetic acid. Sodium acetate is this. And that's how we name these, by the way, carboxylates, okay? You take the IC off and add 8, and then you got to name the metal, whatever the metal is. So this is sodium acetate, okay? And what do you notice there? It's a solid material, okay? So it's the salt form. Looks like table salt. It's this white material, okay? So that's the ionized form. It's been treated with sodium hydroxide before. So you can take acetic acid here, the neutral form, treat it with sodium hydroxide, and make sodium acetate. You got to dry the water or whatever. This is kind of a neat demonstration. This is a solution of supersaturated sodium acetate, okay? That same stuff we were just looking at. But they heat up the solution and add quite a bit. They go beyond the 60 grams per 100 mils. And then if you let it cool down slowly, it will stay in solution. But we can add a little seed crystal here and get it to come out. Let's see, I just added a little bit of seed crystal off the counter there. What do you see? It crystallizing right away. And look at that, all that solid sodium acetate came out of solution, and there's actually just a little bit of water in there if it's super saturated. And it's quite warm right now. It's that heat of solvation you can actually feel, but yeah, another neat demonstration there. Okay, so keep that straight. We have two different forms of carboxylic acid, the neutral protonated form and the salt form. They're very different in properties. Okay, keep that straight. Let's take a break. We'll be back for the second hour. Yep.